Okay, so one-sided communication. This is one of the topics that considered as the advanced topic in MPI. So one-sided communication, or as you may heard, a different word of different terms describe this is called remote memory access (RMA). So comparing to a two-sided communication like a point-to-point. So one-sided communication, basically you have, instead of having two processes involved in the data exchange, you have one process to initiate and do the operation, and also unlike the two-sided communication, you'll be that you have individual you issuing individual operations, and you have to check each one of them, see whether they complete. One-sided communication gives you a way to do a lot of communication and just to complete them all at once, which we'll see in detail. Okay, so the core idea of having one-sided communication is to decouple the data movement from process synchronization. Okay, so this is something like I said. The goal of this is allow you to do a lot of data transfer, and only to synchronize the process for once. So what we do here is what we can do is for each process, they have their own private memory when the process started. Okay, so at a given time, at a given point of the program, then the application can decide, I want to make part of my private memory to be remotely accessible by a remote process. So and basically it's creating this yellow region, and that would, in the MPI one-sided communication, will become a sort of a global address space that is visible by any process that involved in this situation. Okay, so basically for process 0 here, it can access its private memory, and it also can do read and write all the public visible memory from all other process. Okay, so just back again. So every process has decided, I want to expose some memory that allows other people to read and write, and we create a sort of global address space from them, and so that every process can do the access to them. So that's the overall idea of how the data movement is done. So comparing to the two-sided communication, the biggest difference is here. So in two-sided communication, we have two processes participating to do one data exchange. So here we have the right-hand process, which is the receiver in this case, post a receive request, basically saying that if there's data coming in and you need to put all the the incoming data into those two memory segments there. So that's what a receive request or an MPI receive does. Okay, so on the sender side. So sender says, I have some data in these 3 buffers, and I need MPI to send it over to the remote process, the receiver. But the sender would only know that this message goes to this process. Only that process, the receiver process, know where the data should be put in its memory, because those memory are not visible from the sender. So it's a two-party participation. So then the MPI implementation will take the sender request, say, oh, I should gather this data and push it to the network. And on the receiver side, the MPI implementation would receive a bunch of data. And then it will see, oh, there's a receive request. Now the MPI knows the data should go into that memory region. So that's how basically two-sided communication works in MPI. So you need to have two processes, a sender and receiver, to participate in this one send operation. But one-sided communication, because now that each process has exposed a memory segment or memory region that is visible by all of the process. Okay, so instead of saying the receiver or the right-hand process say that the incoming data should goes into this region, the sender can say, I already know where the data is coming from, my buffer, and there's a global visible destination buffer on a remote process. Okay, so I can say I want to put this data into the remote process and go directly to that memory buffer that is visible, globally visible. So as you can see, there's no the right-hand side process doesn't have to do anything explicitly other than exposing the memory region. Okay, it doesn't have to do anything explicitly to say receive these data and put into the memory, because the sender side has already got all the information I needed from its own memory to a remote memory. So there's only one side of this is involved. And also for one-sided communication, we have a slightly different term for describing these two processes. In two-sided, this will be sender and receiver. And in one-sided, this will be, the left one we call it origin, and the right-hand side will be the target. Basically, the origin process is the one that issuing the operation, that is actually doing the MPI one-sided call. And the target side is the process that's hosting the target memory, the memory that you are writing to or read from. Okay, so the why one-sided communication is a good idea is that if you think about two processes doing a send and receive. Okay, the sender can put in information out, and maybe it's already on the network, and maybe even it's in the MPI receive queue on the destination. But the receiver could be delayed by something. I don't know, maybe computation, maybe waiting for other resource to be available. But so that delay could potentially delay the data exchange of this send receive, and assuming if this is a blocking send and receive, then your sender will also be blocked by the receiver side, because receive haven't been able to receive the message. Okay. But with one-sided communication, because the sender has all the information it needs, or the origin process has all the information it needs for the data to go from my memory buffer to a target memory buffer. So it doesn't need the target process to actively involved in completing, saying moving these data into this buffer. Okay, so if there's a delay, it won't affect the data transfer for the origin process. So that's one of the major benefits of having one-sided communication. So in the next few slides, I'm going to talk about the details how we can use RMA or one-sided communication in MPI. Basically, how there's generally there's four main topics. How can the process expose their memory region to let everyone access it, and how to actually access those memory buffer, and how to do data synchronization. And the last part, memory model, it's fairly complex. I don't think I have time to cover that in this talk, but for the simple case or simple application, you don't really need to worry about that, because the basic synchronization and avoiding overlapping the read and write will be sufficient. Okay. So first is how we can create public memory. So as a process, you can just allocate a regular memory using malloc, and those memory will be private. And once that memory is allocated, we can create what we call a window, which is for each process is that yellow region that you're going to expose, the memory region that you're going to expose to others. Okay, so that is in MPI RMA we call it a window. Basically, you'll have a group of process to say I want to contribute some amount of memory into this green global data address space, and saying that's my window to my global remotely accessible memory. So that also means that you don't have to say all the process to create a window. If your application only need this remote memory access on a subset of process, you can have them to create that region, and everyone else could be unaware of it. Okay, but so in order to create the window, there we have 4 different models. We have MPI win allocate. So this is basically say I'm allocating the memory and also creating a window for it. So basically allocate memory and expose to the outside world at the same time. Okay, so that's the simplest case. And then we have MPI win create. This is basically saying I already have the memory allocated. I probably already have a buffer, or maybe my math library has allocated a buffer for me, and I'm going to expose that buffer, and basically creating a window that exposing an already existing memory buffer. And then we have MPI win create dynamic. This is saying I'm going to create a window, and I don't have any buffer to expose yet, but I may have 1 buffer, or I may have a million buffer that I want to put into this window. So you can keep adding new buffers into it, or even remove buffer from it. Okay, so that's more flexible. And the last one, the win allocate share, is more related to the shared memory region. That's basically for the general RMA operation, will be referring to the first 3 window creation models. So as you can see, the lower you go, you have more flexibility, right? You don't, because the first one you have to say I want to allocate buffer and expose them at the same time. And if you do win create dynamic, I can say I have no idea how large the buffer is, and I have no idea how many buffer will there be. But I'm going to eventually expose someone, and so you have the flexibility to do that. But the downside is the more flexibility you got, you have to pay a little bit penalty on performance, because the MPI library has less information to optimize it, right? Because if you have like win allocate, because the library already know you're going to create a new buffer, I'm going to create it for you, okay? And I know how large the memory is. So there's a lot of places that MPI can optimize, while if you do like win create a dynamic, there's much less place to optimize for the library. So far, any questions? Good? Okay. So first, let's talk about MPI win allocate. So this is function. Oh, one thing I have to mention. So the goal of this talk is not to teach you the syntax, but more about the semantics. What we are going to do, because if you are looking for syntax, maybe Google is a much better source than me. Okay, so in order to do win allocate, we need a few things. First is we need a memory size. So this is the size of how many bytes you're going to allocate in this exposed memory, and there's a displacement unit. This is a little bit like data type, but it's not actually like data type. So basically, the idea is you're allocating something like an array. Okay, so you're basically allocating maybe an array of bytes. Then your displacement unit will be like 1. But you can also think I'm allocating an array of integers. So then you have a displacement of unit of 4. Then in the later communication, you can addressing this array using the index rather than calculating the actual address offset. Okay, and there's the MPI info. There's the info hint, which I'll talk about later. And then you need to say which communicator you are creating this window from. So the communicator here basically is just allowing you to say, I want to create this window on a group of process. That group could be a subgroup, could be MPI convert. Then you basically everyone just exposing some memory. But it also could be a subgroup. Like if you just need to exchange these data in a subgroup, you can create a communicator of that subgroup, and then only doing the MPI win allocate on that group. Okay. And the base pointer here is an output argument that basically is the base address of this allocated buffer, and then the window is the handle of the window. That's the MPI object. So the info hint is there's info hint mechanism on all over the place in MPI. So info hint here is basically give you an option that say there's many features in the MPI RMA, and if you can explicitly say I use this feature and I don't use anything else. And with all that info hint, then the MPI library can optimize the operation, and sometimes in some cases you can get maybe you can get performance improvement. Actually, I remember like one hint you can get maybe up to an order of magnitude in improvement in performance. But we'll talk about this later. Yes. Yes. So the question is the WinLocate going to create a MPI window on each of the rank in the communicate? The answer is yes. Okay, here. So basically, this is a WinLocate is a collective call. If you do this on a communicator, it means every rank in that communicator have to at least call this. Although, as you can see here, the requirement of the size is non-negative. So one process can say, I don't want to contribute any memory. I can put 0 here. That's totally fine. Okay. There's actually, I think there are some applications that creates window where there's only one process exposing memory to everyone else, and our process just say, I don't expose. I just read from there, and they all put 0 in there. That's okay, as long as that's and they also have to, as you can see, it doesn't have to be uniform. So one process can say I want 1 megabyte, and the others say I can expose maybe 10 megabytes, something like that. Okay. Any more questions? So here's just an example. Okay. So we have between the MPI init and MPI finalize, we're trying to create a window on top of MPI convert. So basically all the process. Basically what we're trying to do here is we're creating the semantic will be creating each of the process exposing an array of 1,000 integers. And the displacement unit here will be the size of integer, which in this case was 4. And we don't do any special info hint here. And then the A is the memory buffer that getting allocated, and the window. And after that, you can do a bunch of communication and read and write or what. And then at the end of that, you have to free the window, and which also in terms deallocate the memory buffer. So that's when you allocate. Like I said, not every process has to contribute or create 1,000 integers. If one process want just to put 500 integers, that's totally fine. Okay. Any question? So to put the data in the remote buffer, you're going to say that I'm going to put data in this remote process. You need to know the remote process rank, and you also need to know the index of the specific element of that array. Because your remote process is like 1,000 integer, and I can say I want to access a remote process, maybe rank 1 and the 5th element in this array. You can imagine that the array, but you can also like set the displacement unit as byte, right? So that become just like raw memory that you can read and write from. Okay. So the next model is WinCreate. So it's pretty much the same, right? So you still have the size. You still have to specify the size and displacement unit and whatnot. But here the pointer became an input argument, which is you have already allocated this memory buffer, and you just grab that pointer and put it here, and that would expose that memory buffer in this window. And the example would be like I have the example here is using MPI alloc mem, but you can use malloc, you can use calloc, whatever POSIX mem line. You can use all of them. You don't have to use alloc here for new MPI, because that was from MPI 2 back then. There was some requirement. So after you allocate the memory buffer, you can just do regular load store A0 equals 1, something like that. And at some point, you decide, I'm going to expose this memory. And then you do WinCreate with this memory buffer A. And then after that, you can do RMA operation. And then before you exit, you have to free the window, and you also have to free the memory. Okay, so good. And the last one is MPI WinCreate dynamic. So the WinCreate dynamic is fairly simple, and just saying everyone just saying I'm creating a window. This window is empty at this moment. And if you have a buffer that you want to expose through this window, you have to call MPI win attach and detach to put buffer in this window or remove it. And you can keep putting new buffer into it, and so it's sort of expanding the scope of this window. There's no guarantee that, well, basically the library doesn't provide guarantee that your operation on this window will always happen after you attach the buffer. It's the application's responsibility. So you have to algorithmically decide that some process maybe have already put the exposed buffer or attached the buffer to this window, and I know that for sure that's happened. Maybe you can do a barrier, and then I'm going to do RMA, because if you do RMA to a remote window that doesn't have a buffer exposed to it, it's incorrect program. Okay, so the example is fairly simple. We just at the beginning we just create an empty window and allocate memory, and at some time at one moment we just attach this memory buffer A into this window, and also saying this how large is the memory, and then you can do RMA with it. You can attach. Yeah, the question is you can only attach the once, or the answer is you can have multiple buffer. But for one buffer you can only attach it once, right? Because if it's already attached, there's no point of attaching it again. But let's say I have another, after attaching this, I can do another malloc and get a new buffer, and I can attach that new buffer to it, and do read and write. And I can also like detach this buffer A and do some local stuff maybe, and then reattach it. This is all the flexibility of the when created dynamic that provides you. Yes.
Wondering, so what's the downside of not using by default one-sided communication? In other words, can you just by default expose all your memory to instead of just a window, or so basically you replace your code with one-sided communication? What would be the downside on doing that?
Well, actually, I'm not saying that you should always use RMA. Okay, so whether to use RMA, whether to expose this window depends on how your algorithm fits in this one-sided model, or maybe it fits better in the two-sided model.
Would fit in the, suppose that it fits into one-sided model, how would that not fit in two-sided model? That's my thing, because you're just exposing all the memory if you, right?
Oh, so first, it's not exposing all the memory. You're exposing a given amount, right? And so the benefit of having RMA is you basically decoupling the data movement and the synchronization. So generally, if you have a very regular application, like maybe a stencil kernel, it already fits pretty well with two-sided communication. You can do one-sided with them, but there's probably no major benefit. But on the other hand, if you have like a very irregular application, the data access pattern is fairly irregular, then using one-sided might be better, because you don't have to fit your application into this two-sided communication, which sometimes people would refer to it as a box synchronization. So it's just the overhead. So one example that they use one-sided communication is a lot is NWCam. That it's one of the bigger applications that relies on one-sided communication pretty heavily. NWCam. It's a quantum chemistry application. Okay. So the next thing is I should skip. So the next we're going to talk about the data movement. So in this talk, we're going to cover these 6 data movement. Basically, this is how you read and write and doing operation on the remote memory buffer. Okay, we have MPI put get. This is just write and read, and we have the other 4: accumulate, get, accumulate, compare, swap, and fetch and up. So those 4 are what we call the atomic operation in this in the RMA, or as the MPI standard they call it accumulate like, but usually we just call it atomic. Okay, so put basically is you have some data in your origin process, and you want to write it to a remote memory on the target side. So so for this call to work, you need to have an origin address and content data type, and you have a target you have a target rank, and you have a target displacement. So this displacement is what is essentially the index to the element of this array like layout. Okay, and you have a target set count and target data type. So so one thing to there's 2 things I want to talk about. So first is on the issuer side, the process that called the MPI put has all the information, right? Where the data comes from and where eventually it will go into. So that's how it become one-sided communication. So the second thing is the data type here doesn't have to be the same. Okay, so the benefit is that you can do the data transfer while also transpose the data into a different layout. So you can have So for example, if you have like a 2D array and you can send a row, but on the receive side and store them in a column. So basically you have contiguous data but store them into a non-contiguous region. That is something can be done with using different data types. So it doesn't have to be the same. And the last one, of course, is just the window handle. Okay, so that's put. And the opposite will be get. So the operation is like I know there's a remote buffer and described by all the blue argument here. Basically, is describe the target buffer, and I have my own local buffer which described as the green. So the origin process would issue in this call and basically fetch this data from the target buffer into the origin address. Okay. So that's put and get. We have any questions? Good. Okay. So next we're going to talk about the atomic operations. So first is accumulate. Accumulate is basically I have some data in my origin address, and I'm going to do some operation and accumulate it onto a remote buffer. So basically this is reduce the origin data and the target data and then write into the target buffer. So apart from the argument that described the origin buffer and the target buffer, we have an MPI op, which is the same op argument that you use in the collective reduces. So we have MPI sum and others. Okay, so for this one, the basic type elements of these operation has to match. Okay. And apart from that, we also have a special operation called the MPI replace. So what the effect of using MPI replace on this is essentially an atomic put. So basically, I'm taking the target data and not doing any calculation, but just overriding I'm taking the origin data and overriding the target buffer. So this is so in effect you are doing a put, but atomically due to the accumulate semantics. That's a good question. So the question is the operation atomic with respect to individual index or entire window? So the answer is the atomicity is with respect to a single data type element. Okay, so let's say the simplest case, I'm doing accumulate with MPI double. So I'm doing with MPI replace. So I'm doing atomic put of an MPI double. So only that 8 bytes of remote memory is atomic. The atomicity is with respect with that 8 byte data. Okay, not the whole window. So if I'm writing to if I'm doing MPI put on that buffer, and someone else is also doing MPI atomic put on that buffer, these put would result in any order, but you won't have garbage data. Okay, so that's so if you do just regular put, like there's buffer with 0 and 1 doing put 1 and the other doing a put of 2 and trying to override. So the result could be 0, could be 1, could be 2, could be 52, could be anything. But with an atomic put, that buffer will either be 1 or 2. But the other part of the exposed of the window that doesn't involved in this operation, the atomicity doesn't affect them. So you can. But the thing is, because we can do data type, if I do a data type of contiguous of 100 MPI double, the atomicity is with respect of individual of these contiguous type. So you can, if I do put one to all 100 elements, and I have another process doing atomic put two on all these 100 elements. Each of these elements can be can either be one or two at the end of the day. But you might end up with a data array that your 100 element will be like 1, 2, 1, 1, 2, 2, something like that. So it doesn't guarantee all be 1 or all be 2. So it's not. So it's at the single element level if you have a data type. But if for the basic data type is just for that element. Okay. Any more questions? Okay, so the next one is getting accumulate. This is a little bit more complex. So still we have the green and blue, the origin buffer and the target buffer. But now we also have a result address. So what this operation does is I have some data in my origin buffer, and I'm going to do a reduce calculation with the remote data and overriding the the target buffer. But before I'm overriding that, I'm also fetching the original value of the target buffer back into my result buffer, which is described by the result address here. Okay, so it's the same. You can do all the MPI op, and what we provide is a special one is called MPI no op. Basically, is just the effect is I'm not overriding anything. I'm just fetching the target buffer into my result address. Okay, that's the case. Or there's if you do MPI replace here, it will become atomic swap. Basically, I'm fetching the original value from the target buffer to my result buffer, and then I override my value in the origin buffer, the green one, into the target buffer, the blue one. Okay, so this is basically if you do atomic swap, the value of blue goes into the red, and the value of the green goes to the blue. So that's how you can do atomic get and atomic swap. Okay. So the next set is fetch and op and compare swap. So fetch and op is essentially a simple version of get accumulate. Okay, so in this case, it's always there's no count of the operation. If you go back look at the get accumulate, you have a count saying how much data, how many elements that in this data type I'm doing in this operation. But with fetch and op, the number is always 1. And so it's just because it's simpler, it allows me to do some optimization, especially if you have like basic data types. Okay, we can use hardware implementations to do the operation if the network hardware supports that. And the last one is compare swap. Compare swap is basically we also have a compare address. If the origin address and compare address are the same, we're going to override the. We're going to do a swap with the target side. So that's compare and swap. So that's all the semantics of this operation. So one important thing I need to talk about, which I touched a little bit, is the ordering of the operation in RMA. So there's no ordering guarantee of put and get into the same buffer. So anything could happen. Right? You put 1, put 2, and you can your result could be 42. Okay. So But that only happens if you do put and get on the same address. But if it's happened on different address, that's actually because you're not overriding with each other. So it will be fine for most of the time. And then, but if you do atomics, then we do have guaranteeing of ordering. And in fact, we have all the guarantees: read after write, write after read after read, and write after write. So this is where the info hints comes in, becomes important. I remember I mentioned when you create a window, there's info hint that you can provide and tell the MPI library that there's some feature I don't care. So I'm not using it. So this is one of the place. So one way that an application can do is, if I know that my application doesn't need some of these ordering guarantee. For example, I don't need write after write, and I can pass it into a MPI, say using a hint. So the MPI would know, oh, that is not needed, so I can optimize the implementation. So the thing is with some of the hardware, the write after read was pretty hard to implement. In fact, there's no hardware support for that. Not even on not even on QPI. So if you use all of them, what MPI have to do is you have to emulate all these ordering in software. But if I tell the MPI that I don't need some of these guarantee, then MPI can figure out, oh, then I can implement the whole thing in hardware semantics, and then the operation becomes much faster. So the rule of thumb is, when you write your program, always try to give this hint. There's practically no downside of it, because if you're hinting this, basically you're saying this feature I don't care. And if the library can optimize on all of them, then you get performance boost. And if the libraries say I don't do any optimizing, I'm going to ignore a hint, you don't get any downside, right? Because your program still work, and the part that you don't use, it's just, no matter how the implementation does it, it doesn't affect you. But if the application really read into these hints and try to optimize it, you get automated performance boost. Okay, so just some quick example. So the process you're trying to do operation on the same memory location. Okay, so if you do two puts, the result will be undefined. And put get is the put accumulate. If you do a non-atomic operation and the atomic operation, if you mix them together, this result will still be undefined. The ordering is only guaranteed for all the atomic operations when you do this. So this is strictly inside related to the synchronization model, because the atomicity only guarantees within the same epoch if you do atomic operations. Okay, so that's a window creation and data movement. Do we have any question about that? Okay, so the last thing I want to talk about is RMA synchronization. So first of all the RMA data movement operations are non-blocking. There's no blocking, put, blocking, get. Everything is non-blocking. But as you may have noticed, they are non-blocking, but they don't give you an MPI request object. So you don't have a request to look into whether this operation is finished. So how do I know if the operation has been completed? That's where the RMA synchronization model comes in. So to be clear, the synchronization here, basically we're synchronized the memory operation. So what it means is after the synchronization, your memory, all the read and write has taken place, and your memory, the data is in a consistent state. Okay, so it's not like doing a collective synchronization like using MPI barrier, because that's synchronizing process that doesn't synchronize the actual memory access. Okay, so this is synchronizing memory access, not process. So if you want, when you're using RMA, if you really need to synchronize the process and make sure that everyone is at the same place, you still have to use an MPI barrier. You cannot rely on the RMA synchronization to do that. So just to make that clear. So we have 3 different synchronization models. We have fence and we have post-start complete wait, which is a more generalized version of fence, but honestly it's not very. It's a little bit complex. I probably won't cover this in this tutorial. And the last one is a lock and unlock model. So basically, what this synchronization does is it will open what we call an epoch. So in the MPI's term, before you do anything, any RMA operation, you have to open an epoch. It's like saying I'm starting doing an RMA operation, and then I do a bunch of RMA operation, put and get, accumulates, and then I have to close the epoch. So what the MPI library would gives you is when you close the epoch, it will guarantee you that all these operation has been synchronized, your memory in a consistent state. So basically, there's you have to so all the synchronization model here basically what is give you an opening of an epoch that you can do operations and close it, synchronize the state. Okay. So the first one is fence. Fence, you just need to use this MPI win fence function on a given window. So like I said, before you do MPI, the RMA operations, like the red one here, you need to call fence to open an epoch, basically saying, I'm starting to do RMA operation. And this is actually a collective call. So every process in this window need to call it. So everyone has a start point and say, this is where the operations can happen. Okay, and after calling that, you can do all different put and get. In this case, so between these 3 processes, there's a lot of put and get going on. And again, as long as your operation with regular put and get, as long as you're not operating on the same memory address, it's okay. And then after all the operation has been issued, and everyone will call MPI win fence to do another fence call, and this may take a little bit of time because some of the operation may not be completed yet. But eventually, when the fence call is returned, then you know all these operation has been completed, and my memory is in the consistent state, and I can keep doing whatever other operations. So one thing you can do is you can even after this second fence you can do more operations and call fence again. Then it's sort of like if you have something that it's conflicting with the previous operation, then you can do like after the second fence, and then keep and calling another fence to complete that. So it is sort of like wait, but like I said, it's not synchronizing the process. It's just to synchronize the memory operation. So with the fence model, one thing we can do is if we think about our stencil example, we can implement the point. We can change the point version and implement using RMA fences. So essentially, for each of the process, it can expose its it's the data region as in RMA window. And then during the halo exchange, your boundary and the halo region will become the origin buffer and target buffer. And each process will put their boundary into the halo regions of the neighbors. Okay. And we actually planned an exercise with this. Basically, you can take the derived data type version and trying to convert it into a stencil fence version, and we have a solution in there. But we can do this in the hands-on time. So that's fence. Okay, so the other model I'm going to talk about is the lock-on-lock. So the fence model, like I said, the fence call is collective. So everyone have to call the fence and start the epoch and doing operation. But being a irregular application, that may not be the ideal case, because maybe not every process need to do operations at this period. So making them all calling fence is kind of awkward, and it's certainly not optimal. And so we have another model we called lock and unlock. This is a little more like memory. So the first thing, the lock unlock here, it does not involve. It's just the naming. It's not involving anything mutex or lock. It's not a lock in the Euro sense. It's just the naming. Okay, so. The one very important thing is using lock unlock basically is your essentially is your origin process say I want to do some operations on a target memory. So I kind of doing a lock and let everyone know that I'm doing operations on this remote window. So everyone knows that there's some operation happens on it, and but the good thing is the target don't need to participate and say acknowledge that I know you're doing operations on me. It doesn't have to explicitly do that. Okay, so I don't have to make anyone else to sync with me and to do this. Okay, so basically, is the lock unlock is basically begin and it's the begin and the end of the epoch. So for the origin process, you will have to say I want to lock a target rank on this window, and I'm going to provide a argument here. It's called lock type. There's two types of lock in MPI. So there's shared lock, and there's exclusive lock. Okay, so if you do shared lock, it means I can lock on this window, and someone else can also do this lock share on this window, and they both can access this window. But then the downside is if they all do put at the same time, it could be generating garbage data. So that's why there's also exclusive lock. Basically, if I lock this window exclusively, I lock this target window exclusively, then no one else can lock on it before I unlock. Okay, so that guarantees exclusive access to that window, and I can safely do put and get without using the atomic. Okay, and if you have like multiple operations, you don't have to, and on the same window, you don't have to do lock unlock repeatedly for different operations. Okay. So you can do lock one time and do some operation, and if you want to make sure that the operation is completed, there's a flush. There's MPI win flush call that you can call. Basically, it's essentially just completing all the operation that has already been issued. And after that, you can issue new calls and on overlapping address, which would be no problem. And only and after you doing all this operation, and you can call the unlock, which will automatically flush the operations. And in some other cases, we also have lock on and unlock on. Basically, this instead of locking one target, the window of one target process, this locks all the process in this window. Okay, and there's also a flush all and the flush local to do that. Oh, I didn't mention the flush local features, right? So we have flush to complete the RMA operations. That completion is guarantee your operation has been issued and it has been completed on the remote side. But there's a lighter call for that is called flush local. So basically, the flush local is what it gives you is your operation has been issued. It may or may not be completed on the remote side, but I don't care about that because I can issue more operation locally after that. But remember that when you call flush local, the data may not be updated on remote memory, so you should not try to override it at that time because it could still ended up in throughput not being in correct order. Okay, so as I mentioned, there's one of the example that use RMA a lot is NWChem. So it's a quantum chemistry application. So what NWChem does is each process has this has a sparse matrix, and they put into this global address, so they have irregular access to a large amount of these data. So each process can just do fetch. So their kernel is actually is doing this get compute update. So what happens is because these are large sparse matrix, so it's very inefficient to just do the regular matrix optimization. So what it does, it will divide the matrix in blocks, and if they only do calculations on the blocks that is non-zero, so that's basically you ended up with depending on how the matrix looks like, you ended up with all different kind of pattern that you don't have a really regular pattern to access it. So that's how RMA become quite useful in this case. Okay, so I guess I think there's a question asked about whether I should use RMA or how can I use it. So just to summarize, RMA usually has lower overhead versus send receive because you have this decoupled synchronization on, and they also map directly to the RDMA semantics. But I have to point out here, it doesn't mean that you can only use RDMA with put and get. If you do send and receive, the underlying communication will still be performed using RDMA if you have InfiniBand and through network. We're using that using low level library. So whether to use RMA it solely depends on what is the algorithm that you develop for your application. Whether this application fits better in a box synchronized model or it's more irregular that you want to consider RMA. So if you decide to use RMA, you need to make the choice to whether use the fence synchronization model or you want to use the lock and unlock. You can mix them in one application, but depending on how your application goes. For example, if I have like a box synchronization, like you can think about using fence because fence is collective. Everyone has to call it before doing any operation. So if you only have one process is doing the put and get, it's creating overhead and synchronization point to force everyone to go into this fence. Okay, so in that case, you might want to try the passive model, doing lock unlock, just for just to lock and unlock the target window that you actually doing the RMA operations on. Okay, so I think that's all my slides. Yeah. So again, we have this hands-on example for you to use to create an RMA version of the stencil based on the derived data type one. And I think we also have more advanced. If you're done with that, you can also try to use a lock and unlock model to implement it. All right, so that's all I'm going to cover with the RMA stuff. And if you have any questions, I'm happy to answer. Or otherwise, I can give the stage back to Giuseppe, who will talk about the MPI plus acceleration.